Hello everyone. Today in this lecture we are going to deal with the non-coherent modulation. Till we in the earlier lectures, that lecture 5, lecture 4, lecture 3 and lecture 2, we deal with the non-coherent type of we deal with the coherent type of modulation. So what was the coherent modulation? We had a additional reference signal which used to be used in the transmitter and which is also be used in the receiver to nullify and to have the synchronized reference. But in this non-coherent orthogonal modulation technique, you can see here, that is what I am telling you. In coherent demodulation thing, it is required to have a local reference signal at the receiver which is in agreement with the phase of the carrier. That is the carrier signal what it was is to utilize over there. But some demodulation schemes do not require a local reference signal, that is in synchronize with the received carrier. So that we call, that doesn't require a carrier the synchronization or a local reference signal. So we call those schemes as a non-coherent scheme. Non-coherent schemes are used when the knowledge of the phase carrier is not available at the receiver. Okay, that we don't require any kind of a phase carrier, whatever the knowledge of the carrier signal phase. In non-coherent system, the structure of the receiver is simple compared to the coherent system. We don't have additional big the structure, the correlators, etc. We don't require. That's a simple coherent system. Okay, when compared to the coherent system, it is very simple. Under this large signal to noise ratio, the performance of the non-coherent receiver approach that of the coherent receiver. So that is what this is. The performance of the non-coherent receiver also is better when compared to the coherent receiver. We'll see. We have to deal with the two types. One is the FSK, another is the DPSK. The first one is the FSK. In the lecture 5, we deal with the coherent detection. Here we are going to deal with the non-coherent detection. Here, first the signal whatever is being sent has been matched with the filter thing. Okay, whatever the filter has been matched. So it is trying to see which is designed for S1 of t and S2 of t. Okay, then it is followed by the envelope detector. So what is doing here, it is trying to match and compare with the design there. So it is trying to compare with the F1 and this is with the F2. The F1 is the higher frequency component, F2 is the low frequency component. So this is what we are designed. The filters is like set for F1 of, and here is for F2. You know what I mean by filter, as we have studied in the DSP and in the signal sense system. So we can design a filter where it can set for only to pass on the F1 of frequency F1 through here and only frequency F2, and that has been detected by this envelope detector. Okay, by this envelope detector. So, and it is sampled at a t is equals to capital T. So what is the time interval given there? That's the same time given. And it is comparing the L1 and L2. How it is comparing? If L1 of is greater than L2, we choose that S1 of. If L2 is greater than L1, then we choose the X2 of T. So here one confusion arises. How it will be there? Okay, you can see here that if a frequency is bit has been sent, if it is having the F1 of t, only this signal will be passed and this will not pass. So that time this L1 greater than L2 it will be. If a bit 0 has been sent here, only this signal has been passed, so that time L2 will be greater than L1 it will be there. So this the filter here plays the big role here. Okay, and this what is the transmitted signal what we have V1 got here, which is represented by Si of t, that is equals to square root of 2 EB by TB into cos 2 pi Fi of t, which is lies between 0 to TB, the small t, and whether other than it's alpha 0 it is. So depending on this f1 of t, this will pass, f2 of t, this will pass. If this is pass, L1 greater than L2, so S1 of t as per logic correct. And if this is pass, the time L2 greater than of L1. So this will be the logic correct. Okay, this is how we represent this thing. Okay, this is what I am explained here. Here, the receiver consists of a pair of matched filters followed by envelope detectors. The filter in the upper path of the receiver is matched to cos 2 pi f1 of t, and filter in the lower path is matched to cos 2 pi f2 of t for signaling interval 0 to tb of small t, which is represented by small t. The resulting envelope detector outputs are sampled at t is equals to tb and their values have been compared. That is what I am told. And the envelope samples of the upper and the lower pass are L1 and L2. The receiver decides in favor of 1 if L1 greater than L2 and in favor of 0 if L2 greater than L1. If L1 is equals to L1, that one complication will definitely lie. The receiver simply guesses randomly in favor of symbol or 1 or 0. It can. So here some kind of a glitch might occur. The probability of error, this is what the problem. So in order to determine the non-coherent orthogonal modulation, the error t is equals to tb and e is equals to eb, where eb is the signal energy per bit. We call this one as the bit error rate of a non-coherent binary FSK is pe is equals to half into exponential of minus eb divided by 2n0. Okay, this is all about the FSK. Just we need to know the structure diagram and how is the working principle carried out, and if the error occurs when L1 is equals to L2, so that time we need to check whether it is correct or not by this probability of error equation. Next, another is the differential phase shift gain. DPSK is non-coherent version of binary PSK. Okay, it's a combination of, you can see here, if we remove only this much, this is a phase shift gain with a differentially encoding technique. Okay, here DPSK eliminates the need for this synchronizing the receiver to transmitter by combining two basic operations at the transmitter. Okay, so what is this component here? Usually what it is doing, in the PSK we require a basis function which has to be used in the transmitter also, and it is to be used in the receiver also. But what is happening here, this differential encoding sequence which is getting added and then PSK is done, the PSK principle has been done, and that time what is the output you are getting, and this causing this is helping us to avoid the need of a synchronizing. Okay, how this is done? First we differentially encode the input binary sequence, and then we go for the PSK encoding sequence. Here differentially encoding sequence starts with an arbitrary first bit serving as the reference bit. We have to take one reference bit. Usually this concept is little bit in confusion when we explain it theoretically, so I'll just go in brief about this theory here, but when we go to the problem we'll go in detail. Okay, so to this end the symbol 1 is used as a reference bit. Usually generation of differentially encoded sequence then proceeds in accordance with the two-part encoding rule as follows. If a new bit at the transmitter input is 1, leave the differentially encoded symbol unchanged with respect to the current bit. If on the other hand the input bit is 0, change the differentially encoded symbol with respect to the current bit. So what is trying to say, that is if a bit 1 has been given, the reference bit is 1 and the input is 1. When it is multiplied 1 and 1, it has to be same. The current and nothing will be changed and nothing will be. So 1, we go for this condition 1 and 1. So that time it should be 1 only. If a input is 0 and reference bit is 1, so that time it is the symbol is being changed. So change to the current bit, that is 0. Okay. The differentially encoded sequence is denoted dk, is used to shift the sinusoidal carrier phase by 0. That is, if shifted is by if that bit what we getting at a decay, if it is a 1 or 0, if it is we are getting a decay as 1, the in differential encoder sequence output as 1, we represent it as 0 shift, phase shifting. If it is a having a symbol 0, for example it is having a 0, decay is equals to 0, then it has to be phase shifted by 180 degrees. That's what we usually do in the PSK. So this is what I'm telling. So before reading this DPSK, please have a brief idea about PSK. Okay, else it will be confusing. If you know the PSK, this is very easy to solve. Thus, in terms of the phase shifts, the resulting DPSK signal can follow following phases. To send symbol 1, the phase of the DPSK signal remains unchanged, as that I said, just 0. To send symbol 0, the phase of the DPSK signal shifted by 180 degrees. That is what I am telling. Okay, so in problems we can solve it very clearly. So just this much you have to be known. That is, to send symbol 0, 1, the phase will unchanged. The phase shift will be 0. To send symbol 0, it has to phase shift by 180 degree. Okay, and when you compare to the reference bit, when it has to be the similar bits are there, and both are similar bit, that is the input sequence and the decay that's is compared with the 0 or 1 reference bit. So depending on that we have to take. Okay, I'll not put more light on it. We'll go to the block diagram for that I need to. If a DPSK is an example of a non-coherent orthogonal modulation where its behavior is considered over the successive 2-bit intervals, that is a 0 to t and 2 to b, because we will be considering dk and dk minus 1. So that is the reason I told we'll go to the block diagram directly. Okay, see here, if it is a bit 1, square root of eb by 2b cos 2 pi fct, if for symbol 1 for 0 to tb, and also square root of 2 eb by tb cos 2 pi fct symbol 1, because here we comparing with the 2 bits here. One is a dk and dk minus 1, symbol 1 for tb over t and 2 tb. So that is the comparison. So s1 of t is represented for a successive 2 bits which are of the same symbol, that is no phase change. So here no phase change because both here are transmitting symbol 1 and the same thing is there. So you can see it here that if a symbol 0 has been transmitted, pi has been added. Okay, so when compared to the others, the signal there, that symbol 1 was transmitted, so that time it was the same thing, cos 2 pi fct, cos 2 pi fct, but here symbol 0 has been sent. So as per our DPSK rules, plus pi has been added, which is that, and 2-bit interval, the 0 to tb and tb from 2 tb. So this is a 2-bit interval, 0 to 2 tb. We have sending a 2-bit symbol 1 and symbol 0, but earlier we sent symbol 1 and symbol 1. So this is how we can tell that a carrier signal has been added with a pi. So that is symbol 0 has been sent. For DPSK, how to find the probability of error? For earlier condition, what we use it for FSK there, we represented t is equals to with respect to 2 tb and e is equals to 2 eb because of this condition, the above condition. We have used it for 2 tb, the time duration. E is also for 2 eb because we are representing the 2 bits. So see here that p is equals to 1 by 2 exponential of minus eb by n naught, because 2 and 2 by 2 will get cancelled. Okay, so that is the p is equals to half into the exponential of minus eb by n naught. Next, the generation of a DPSK signal. How this DPSK signal has been generated. So this is what the main, what I need to be explained here. Here, what it is representing, the transistor consists of a 2 functional blocks here. One is a logic network and 1-bit delay storage element, which are interconnected so as to convert the raw input binary sequence BK into the differential encoded sequence DK. Okay, so see here, so we take it as a BK, 1 bit we are sending here, but what is happening, we need to have a DK minus 1, so that is the reason we are not getting here. So what we take it as a reference bit as 1. That is what I told, 1, and what is the bit will get multiplied and we send. So how it is the functioning here? So it will be an XNOR bit. That is the, if it is 1 and the reference bit I have taken it 1 here, so it will be 1 here. So 1 and 1 So what it is giving now here is 1. Next bit is 0. Okay, and what is this 1? With decay, and it is sent here. It will become 1. 0 and 1, what will become next function? 0 and 1, it will become 0. So what is this now? This is nothing but the XNOR function, and there is a similar bits 1 1 or 0 0. The output will become 1. That is a decay will become 1. If it is 0 1 or 1 0, the bit will become 0. So similar bits will get the decay as 1, and unsimilar bits will get as a decay as 0. So that is what the reason I took it a 2 bit here. We consider it as a 2 TB, because one bit is sent here, as one bit is sent here, another bit has been taken here. So that is the reason we consider it for 2 bit, and also we do it for the differential encoding XNOR sequence. So that is the reason we get a 2 bit sequence here. And after that, the normally we go for PSK, whether it is bit 1, it will become, if it is a bit 1, that time it will be a no phase shift, that is a 0 degree. And when if it is a bit 0 or bit 0, pi, it is multiplied. This is the same as the PSK. The amplitude level, depending on the 1, it is getting multiplied and it is sending. And if it is 0, then it is amplitude level shifting. It is telling that whether it is a square root of EB or minus, so that is going to tell. Then this is what we are getting in DPSK. So in general, what we can say that this is nothing but here this is a differentially encoded sequence here 1, and this is a PSK. So together we call this one as a DPSK. Okay, together we call this one as a DPSK. Understood? This is together we calling this as a DPSK, differential encodation combined with the phase shifting. Now we have to detect it. How to detect those things? Okay, that will come. The optimum receiver of the detection of DPSK. Remember, this is a non-coherent here. It is a non-coherent. So here the optimum for the here block diagram has been given. It has to be optimum, because it is the optimum, because in the structural term the receiver avoids the use of the fancy delay line that could be needed. Otherwise, in operational terms, that the receiver makes the decoding analysis straightforward to handle, in that the two signals to be considered are orthogonal over the interval 0 to 2 TB. So what is happening here? So what we are sending a signal, one is sent here, another is here. Okay, so cos 2 pi CFT is given, and one is given here, multiplied and passed on here. Another is provided with a minus 90 degree phase shift, and it has been given here. That is multiplied with the sign. Okay, that is multiplied with the sign. So you remember that if it is a bit 1, so that time it is getting multiplied, the carrier signal will get cancelled, and that is given here, and the delay, and it is also the delay bit also getting cancelled. The decoding sequence has been removed off here. The same thing will be taken here and delayed here. Okay, similarly, if it is a 0 bit, it has been considered here, so it has been multiplied and been passed here. So what is happening here? Here what we have done it as a differential encoding, we getting it again, we cancelling each other with the same, delaying the 1 bit there. That what we had done earlier. So delaying process, this is with respect to the PSK what we are doing, and this is with respect to the differential. So delaying sequence and getting cancelling each other is done here, and we can pass on here. So together that is been checked, and checking for whether it is the same one, if it is y greater than 0, and if 0, y less than 0. Okay, so this is, we need not too much worry about it, just we need to know how the principle is done. So how we are done the differentially encode, then apply it for the PSK modulation. That's a PSK we do. Here first we remove the the carrier signals. So that is we are done here, that we do here, and then again multiply, and the same thing we have delaying here, so that we can remove the differential encoded signal. We did not study too much on this thing, because we have one problem to solve. We can see in the next lecture we'll solve our problems in a detailed manner. Okay, so just remember this concept. So, and we don't have any too much derivation or anything, only this much as per this syllabus. Thank you.